Let us begin with a little bit of a review from last time and then into the new stuff. So let us remind ourselves where we ended, or what we kind of covered before, which is this, I guess, topic of what we call evaluating predictors or models. So like this is, we had this learner, this ERM learner, it produces a predictor, and we just want to know, like, did it do a good job? Did it produce a good predictor? And so that's what we were trying to get to the bottom of, kind of. And like, the way to do it was, I guess, sort of straightforward. It was like our ERM learner produces some f hat, right? Produce some f hat. And that thing has like some estimated loss, which is what it was optimizing over. And the thing we want to ask was like, how close is it to the true expected loss thing? And in particular, we want to ask like, how close is this estimated thing to the true expected loss? Like, how close are these two things? And then we also want to know like, how small is the true expected loss of this thing? Okay. And the way we did this was first we asked how close these two things are. Okay, and then we saw some plots and things, and we basically got to the point that these two guys, which is the like expected loss compared to the estimated loss, how close they are is a function of the function class. So if the function class gets more complex or larger, then they get farther apart. So they're worse, it's a worse estimate. However, if you increase the number of samples, it gets better. And then kind of like the natural next question was like, okay, like just looking at this, if I want the estimate to be as close as possible, what I would do is I would make n as large as possible, but maybe that's not usually like an option that's available to you. So then what you would do is you would try to make f as simple as possible, because if f is really, really simple, then you just have a really good estimate. And then what we find is that maybe that's not such a good idea when we start considering, okay, there's these plots, when we start considering the fact that we want the expected loss to be small. Like, we don't just want our estimate to be close to the true expected loss, but we want the actual expected loss to be small. And so for that, we got to this like decomposition of the expected loss of L hat. Sorry, this expected loss of our actual predictor. And what we found is there's like this trade-off of two things. There's this estimation error and this approximation error. Okay, and in particular, what we saw is that we could think of the approximation or the estimation error as exactly this difference between the estimated loss and the expected loss that we saw above. Okay, and so then you really see that there's this trade-off between, if you want to make this thing small, what you would do is you would pick a simple function class. That means your estimates are good because there's very little functions that you need to estimate in some sense. However, what you trade off is the fact that the best possible function in your function class, f star, is now really, really far from the best possible function from any function class, which is this f base. So yeah, simple function class, this is small, while this guy, this approximation error, is large, and vice versa. So there's this trade-off. And the way we saw this was like through this very complicated looking plot now, I guess. But the story was that if you increase the complexity of the function class, or the size, this p, then what you will find is that essentially at the beginning, you just kind of suck, but then as time goes on, things get better. So this is like the actual expected loss of our predictor gets better. But then if you get too complex, then you end up getting worse. And this was basically this trade-off between how large you make the approximation error and the estimation error. So they're always battling between each other, and there's like a good middle point. Okay. And then like I want to just highlight what it means, like what's actually just like kind of going on in terms of like in practice, what are you doing here? What you're doing here is you try to decide what learner you want to use, in the sense that like what function class are you going to use for your ERM, right? So like if you're running ERM, you need to pick a function class that you're optimizing over. And this so this is telling you like what is the function class you should pick for your ERM learner. So how you're actually implementing this stuff is that you run the ERM learner with a function class that's polynomials of degree 1. Then and that produces a predictor, and that predictor would have like this corresponding. Oh, actually, maybe I should get to the case with the test and train stuff. So let me maybe mention that briefly first. But like, so in reality, you don't have this expected loss. So what you do is you estimate it with this test set. Okay, maybe before I say that, let me come back to this. So we have this learner. We want to know what function class we use for it. So what we do is we just try a bunch of different function classes. We try like the polynomials of degree 1, 2, 3, 4, 5 onwards. And for each one of these, our learner will produce a predictor, right? And if we knew the true expected loss, which is this guy, we would just like plot those values. And we would see something like this. And this, I guess, is what you're going to see in your assignment. And you see this thing, and then you're like, okay, so I have these predictors, which was trained in this case, I would have had 7 learners that each produced a different predictor. And then I look at their expected losses, and what I do is I pick the one that has the smallest expected loss. Okay, so you really, in some sense, there's like this kind of like meta algorithm going on, which is actually training 7 learners. Each of them produces a predictor. You evaluate each predictor, and then you pick the best one. Okay, so that's what you want to do. And then there was this observation that, okay, we don't have the expected loss, L. So what are we going to do? Like, this plot is all great and wonderful, and we picked this thing, but we don't have this function. So we solved this problem by estimating that function, but estimating it with a new set of samples. And then we mentioned, oh, we can't really gather new data. So what we do is we like simulate this with our actual data, and we say, okay, we're only going to train our learner. So like our learner is only going to use dtrain. We're going to split our data set into 2 chunks, dtrain and dtest, and our learner is only going to use dtrain. And so what that means is this, like the remaining part of the data set is not used by our learner. And so in that sense, the predictor that the learner picks is going to be independent of that test data. And so from things we saw earlier, that means that is, if we use that test data, that will give us a good estimate of the true expected loss. And so, and that should like kind of be intuitive. It's like, what happened? I'm clearly in the meeting. Let's have a look. Oh. But the weird thing is I can see my screen on the call apparently. Okay, let's retry joining. Okay, now I'm gone. Okay, I think we should be back. Yeah, now I think we should be back. Okay, anyways, we were at this point of saying that, yeah, we have this training set, and like the intuition is you have this training set, that's what your learner uses to produce its predictor. Then you have a predictor, and then you want to evaluate that predictor. So what do? You go use some new data, which you saved for exactly this purpose, which is called your testing data. And that's going to be used to evaluate your predictor in the sense that that'll give us a good estimate of the true expected loss. And so what we will get is for like a particular data set, you should see something like very similar to what we saw before, which is if you plot the training of your learner, you'll see that if the learner used a larger function class, of course, it's going to get a smaller estimated loss. It just has more functions to pick from. However, what you'll find is that this test loss, which is now a good estimate of the true expected loss, has this shape that we saw before. And so we can use this curve to pick the function class that we should be using for our learner. And since we've already trained these learner, we would just pick the predictor that the learner that used function class of polynomials of degree 4 has output. Okay, so so that's how you do things in practice, and that's how what you'll see in the assignment. You'll see this like you actually do this. You train a learner with different function class sizes, and then you see this curve, and then what you'll do is you'll plot this bottom point, and then you'll plot some other predictors that you get like here or here. And what you'll find is visually that this one fits the data better in some sense. So it looks, or I should say, this point actually is closer to F Bayes than this predictor or this predictor. And that's what you'd want. You want to get as close as possible to F Bayes. Like F Bayes is the best possible predictor you can get. Okay, and then we ended with this point of talking about, okay, we had this like approximation, estimation error, trade-off, business, and thinking about that. It turns out that another common way to think about this is this thing called a bias variance trade-off, and it's very similar. Instead of estimation approximation error, there's going to be this thing called bias and variance, which we now talk about. Okay. Okay, I'll make myself a little bit louder, hopefully. So how do we do this bias variance thing? And it's the decomposition is kind of a similar story. So we start with this thing, which is our objective to make small for our learner. And then we're trying to decompose it into some different error terms that for purposes we'll see in just a couple pages, this thing called regularization. We're going to see this thing called regularization. And there, it'll be useful to think about regularization as trading off bias and variance. Okay, so that's why we're kind of introducing this. Okay, so let's talk about this decomposition. So we start with this guy, and then what we do is, just like before, we actually just add and subtract this expected loss of f base. Okay, this was like the irreducible error, and you see here already that we're going to get left with this irreducible error. What is left is to talk about how we're going to like compare these two, which is the expected loss of our predictor compared to the best possible expected loss. Okay. And so for this decomposition, you need to make an assumption, and that is okay. You need to it technically is an assumption. You have to assume that the loss function you're using is called the squared loss. If you use the 0,1 loss, you wouldn't get quite a nice decomposition like this. But you get something kind of similar. But anyway, so we assume the squared loss, which is what we've been working with anyway. So like for us, it's we're not at a loss quite yet. So okay, so we make that assumption. And then after quite a few steps, which I will not be mentioning in this lecture, but maybe I will help you work through it in the assignment or something like this. But anyways, the point of the story is just assume this is true, which is that after some math steps, so from here to here, you get these two terms. So these two terms came from these two terms. So you do some math, you get these two terms. Okay, what are these two terms? So to understand the terms, you need to understand what is this f bar that appears in both cases. So you can see, like you had this f hat guy, f base. Now we're comparing f hat to f bar, comparing f bar to f base. So what is f bar? Okay, and f bar is in some sense like the kind of the counterpart to this f star we had before, right? So f star was like the best function from our function class that minimizes the expected loss. Okay, so now f bar is not that, but it's something different. But we'll see there's like a relationship. Okay, so f bar is this thing called the expected predictor. Okay, so this is like the actual predictor we output. Then f bar is going to be the expected predictor. So notice how here this is like, so we have f hat and its expected value over all possible data sets. Okay, so let me just rephrase that one more time. So this thing is a predictor, meaning it takes in a feature, right? But it's made up of f hat and its expected value over all data sets. So like for different data sets, you're going to get a different predictor f hat. This f bar is just the expected predictor over all the data sets. And the way you think about this is that you fix okay, so let's just, I know one thing. Here you think of like, it's the expected value conditioned on x, the feature. What does that mean? That means you can think about it in this way. You fix an x, right? Then your function is just takes on values for that fixed x. And then you take its expected value. So that's what's going on here. Visually, you can think about it like this. So like the expected value is taking the f hat over all data sets. So I can't really draw, but what I can do is I can give you some examples, like some samples from the data sets. So imagine we had like 4 data sets like these. And we get different f hats, of course, for each data set, right? And so what's going on here is this expected value is saying condition on x. So like fix some x point. Say like, what's the color? Okay, black. Fix some like point x, maybe like here, let's say. And then go up here and look at all the function values. So look at this function value for the purple data set, and then look at this function value for the dark green data set, and then look at this function value for the red and then the orange, and take basically their average. And you do this in the infinite case of infinite data. That's what the expectation over data is. So this is what it means by the expected predictor. So like for every single value of x, take the expectation over the actual predictor you output, which is different for different data sets. And yeah, okay. So the reason I'm saying this is this thing can be, I think, much more confusing than what f star was, right? Okay. So that is what f bar is. It is dependent on f hat. Like if your f hat is really, really bad, then okay, like the expected thing over it is just still going to be bad in some sense. But okay, so that's what the f bar thing is. So then I guess let me just mention what this variance and bias thing is. So variance is the comparison of f hat to f bar. So it's the predictor you output relative to the expected predictor. Another way of saying, and it's the squared thing. And what you might notice is this is exactly what we saw before of like what is a variance of a random variable. It's exactly saying how much does f hat variate or like differ from the expected predictor, so it's expected value squared, and that's exactly the variance. So this is why it's called the variance. It's the variance of our predictor. How does it vary across data sets? Okay. And then there's this thing called the bias, which tells us, maybe bias is also like a familiar English word. It has also a mathematical, like a mathematical representation, which we won't get into much detail about, but it tells us how far is this expected predictor relative to f base. So like what people say is like how biased is our expected predictor? Like how biased is it from f base? Okay, there's these two terms. Okay, here's a nice special case, which is like if f bar equals to f star that we saw before, right? Then this guy here is actually exactly equal to the estimation error. And this guy here is exactly equal to the approximation error. Okay, so if these two are the same, then you get this thing. So yeah. And notice how like f bar, or like this f hat thing is looking over the same function class as f star was searching over. They're both, yeah. So it's, and in our case, everything we've seen so far, this is actually true. And this shouldn't be so surprising. It's like, okay, on a specific data set, our learner is gonna like vary from f star, but on average, it actually is just going to end up being f star. And I was trying to show this maybe through this plot as well. On average, what you'll find is that f bar is actually exactly f star for the stuff that we've seen so far. And we're gonna see a case in a second where that's not quite true. Okay. So this is what I wanted to say. And it turns out that for this, like, especially in this case with f bar equaling to f star, the effects of changing the function class and the size of your data set have the exact same effects on this bias and variance as they do on the approximation error and the estimation error in like the exact same way. Okay, so first of all, let me say the effects. So bias, as I said, you can think about it as kind of like the approximation error. If you increase the function class, then the bias goes down. Why would that make sense? Well, let's look up here, right? If you increase the function class, then f hat is like your f hat, which is the thing that your learner outputs, has a better function class to look over. So the expected predictor turns out that it will also be closer to f base, because essentially this thing can have better functions to pick from. The function class increases, it's going to have better options. Okay. Then there's the variance case, which is variance will go down if the number of samples goes up. That should make sense. You get more samples, you're expected, like this predictor is not going to vary as much from its expected value. We've kind of seen something like this before. However, the variance will go up, right? The amount your predictor varies from the expected predictor if the function class increases. And this should also kind of like intuitively make sense. As the number of functions increases, then there's a lot more functions that f hat can be, and therefore it's going to vary a lot more from the expected predictor. Okay, so that's kind of like the hand wavy way this is usually explained, and that's how we're going to do it here. But if you think about it with this approximation and estimation error, then maybe it's a little more precise and stuff. Okay, so yeah, this relationship, this kind of behavior is very important in a lot of machine learning. It's like in specifically the way that how do you choose your function class? Because you can see once again there is this trade-off or battle. If you make f large, then bias goes down. However, variance goes up. And yeah, okay. So what happens is that if you plot again, like L hat test and L train, it turns out that like just like before, now you would say that over here you have high bias but low variance, right? This is the case where the function class is small. So function class small means this thing is small, so bias is large, and yeah, okay. So relationship is the same kind of as we saw before. Here we used to have high approximation error. Now it's high bias. And so yeah, you plot this thing and then you end up trying to pick this point. And what people say is you're trading off between high bias or high variance, and you're trying to find the middle point of these two things. Right. And there is one question again before I get to the next part, which is this regularization stuff, which is asking like, can you explain again what the difference between f hat and f bar is? And yes, so the difference is that this f hat is a function of the data. So for each data set, it changes. And so what we can think about is like, if you fix a point x, then for each data set, you're going to get a different value from f hat. Maybe sometimes it might be the same, if you, but like for different d's, you can get different values. And what you want to take is the average value across all possible data sets. If you do that, you get f bar. And visually, you think about it like this. You fix some x, so that's what the conditioning means. And then you look at different f hats, and each of these depend on data sets. So I guess I didn't write about like this guy is dependent on this data set 2, and this guy is dependent on this data set 4, and so on, right? And so you would do this, and you would do this for infinitely many data sets. That's what like this expectation thing is like, if you sample infinitely many data sets and take the average, then what you get is f bar. And what you'll find is f bar is, well, for everything we saw before, it's actually exactly equal to this f star. So you would get this if you do it for every point x. Yeah. Okay. That's bias and variance. And so now we talk about this thing called regularization. And here it'll be helpful to understand bias and variance to talk about this. And yeah. No. This is like, you should think of these as all based on the distribution P of D. So this is like, you get entirely new data sets, nothing based on the data so you only have one. In practice, you only have one of these. But what we're talking about is like, if you were to potentially get just new data set over and over and over again, how much does the predictor you end up outputting basically like change? And that's what, and this gives you the average over all those. Because like, if you had a different data set to begin with, then the predictor your learner produces will probably be different. And then if you had a different one, then you probably produce something different again, and so on. And you want to ask like, on average, what is the predictor you produce? Right? If your learner always outputs the same predictor, then this thing would just be the exact same thing. But like, our learners usually actually change with data. Like if the data changes, then our learner usually actually outputs a different predictor. However, if it were just to always output like the constant one function, then you would have f bar equal to f hat. It just doesn't change with data, but that's usually not the case. So it would have, in that case, like if imagine the learner always outputted 1, it would have no variance. It would never like, it wouldn't vary it at all from its expected predictor. It would always be the same predictor. However, its bias would be really large. Like the constant 1 function is probably very, very far away from f base, which is the best function. Okay, so it's like there's this battle between, yeah, kind of this, we'll see. Okay, so there's regularization. And at a high level, you can think about regularization as giving us like another way to tune the complexity of the predictor we output, but in like a nice, smooth way with a parameter. So what I mean by that is here so far, we've always been talking about changing the function class. And it's been kind of in these discrete jumps of like, you jump from degree 3 polynomials to degree 4 polynomials, and then degree 4 to degree 5, and so on. And this is like, what about the thing where you have some, like somewhere in the middle, where you have some degree 4 polynomials, but not all of them? Maybe that's the best point. Like maybe like in this case, maybe the minimum was actually here, which is something, but like what is that function class? That's, anyways, that's like one maybe simple motivation to think about. Like it would be nice if we just had a parameter that we can really slide to be any possible real number that gives us this trade-off between complexity of predictors, which is really what was going on here. Turns out regularization kind of gives you exactly this. Okay, so what is regularization? So we've always had these like parameters, W. So I'm just defining it. Think of this W parameter as the set of parameters from W0 to W P bar. This is the case of the polynomials, right? In the polynomials, we had P bar indices. So it was like, in the polynomial case, we had R of P bar. Okay. So why am I like pointing out this parameter vector and stuff to you? Well, it's because what you'll observe, like, okay, so this is an observation I'm giving you that there's like some theory and stuff, but like this is kind of like well known, which is that people have found that if these parameters take on large values, okay, if they're large numbers, then what happens is that leads to very complicated looking predictors. Okay, so in particular, this is a predictor that's based on this parameter W. And if those values are very large, like this is like 100 and this is like minus, okay, what I mean by a large, I mean like large in magnitude. So maybe I should make that clear. Like the absolute values of these guys are large. So if you have like one's 100 and then minus 100 and then minus 200 or something like this, what you'll find is that it's very complex. And by complex, roughly speaking, like you can think of it as this is a complex function f. So if you have large wj's, yeah, I put absolute values. If these guys are large, then you have a function that looks like this purple thing. It's like this thing that's very complicated looking. You can think of it as you really need a high order polynomial to approximate it or to represent it. However, if these weights are small, then it turns out G is a simple looking thing, and here maybe you just need a line, like a degree 1 polynomial to represent it. Okay? So this is the like kind of key insight or observation to have in mind. Turns out that if you have the parameter values, like these guys as large numbers, then you have complex predictors. So guess what we're going to do? We're going to add a penalty that we can tune, like a number that basically penalizes having large weights. So the large, like, okay. So that's what's going to happen. We're going to penalize these large weights. That's what regularization is doing. Okay? And we'll see another interpretation of this actually in a couple, like next week on Tuesday. But here's the first one, which is, this is exactly, so it's penalizing large weights. How does this look like? It's like, if you have a polynomial, so this is a function in the degree p polynomial function class, then instead of trying to minimize the usual estimated loss, what we're going to do is we're going to, okay, so what are the usual estimated loss is just this term, right? This is what we've seen before. This is the usual L hat. What we've done is we've added an extra term here. This is called, okay, I tell you the, so this is called the regularizer. So this guy's called the regularizer. So we added this regularizer term. And what is it doing? What it's doing is, so it's squaring the parameter values. So you can think of this as just, it makes the parameter like values positive numbers. You could actually just use absolute values and not use the squared. That is actually a thing that people do as well, but for this course, we're going to just use the squared version. All that it's saying is that if W was large, then this term is large, right? And so if this thing is large, then this term becomes big. But our goal of our learner is going to be to make the estimated loss small. And this thing now becomes called like a regularized. This thing called a regularized estimated loss. So before we had the estimated loss, now we have the regularized estimated loss. And notice that if I make the weights large, like if the learner chooses a predictor that has large weights, then it's going to make this term very large. And then this term, like it's the thing that's trying to minimize would be large. So the learner has to trade off two things. It has to trade off making the actual estimated loss small, while not making this too big, right? So it's like, in other words, it's trying to make the estimated loss small, but only with using really small values of W. And really small values of W, as I said, is basically saying I want to make the estimated loss small with as simple of a predictor as I possibly can. And the trade-off between these two things can be tuned by this parameter here called lambda. And this is called the regularization parameter. Okay, so there's these terms. And this lambda guy is a number between 0 and infinity. Okay, so that's what happens with this regularization stuff. Yeah. Okay. Yeah. Question?
The reason why G
Oh yeah, excellent point. That is one of the things I was supposed to mention, but completely forgot. So notice, so J0 not included is the observation here. Very important. Yeah, so this is important. You don't regularize W0, and like roughly speaking, what does W0 do? W0 only changes how like, yeah, I draw something and then maybe I erase it. It's like if you have a plot like this is what W0 would be. It just shifts your line or your plane or whatever your function is up and down. That's all it allows you to do. If you didn't have a W0 parameter, like this is called the bias term. If there was no bias, you'd always be stuck with functions that go through the origin. So we want W0 to be, first of all, we want to include W0. That's what we've always been doing. But the question is like, why don't I regularize it? And roughly speaking, it turns out that like W0 doesn't actually affect the complexity of like the function, in the sense that the complexity of the function we're kind of seeing is usually governed by something like what's its slope and curvature and stuff like that. And that is really determined by all the other parameters. Where it goes through the origin doesn't really affect how like if it passes through the origin higher, it doesn't really mean it's more complex or not. So that's the kind of the reason why you don't include W0. So, but yeah, that's important because like we're going to see this in a second. When we try to minimize this, and how are we going to minimize it? We're going to solve for the W that gives the argmin, so we'll take some derivatives and so on. This is not going to include W0. Okay. Yeah, let's move on. So the obvious next, okay, like what we're going to try to do is minimize this guy, right? We've been minimizing this before. Now we're going to minimize this new objective. And what we should see is if we minimize this, we end up with a predictor that is kind of as simple as possible while still making this estimated loss small. So this version of minimizing this regularized estimated loss instead of the original estimated loss, this is now called ridge regression, it turns out. This is the name for it. Okay. And before doing that, I just want to give some like observations about why this bias variance thing was important before and how this parameter lambda gives you a trade-off between bias and variance in some way. Okay, so suppose that the minimizer of this regularized loss is f hat of lambda, right? So I'm just putting lambda as like the predictor you get from minimizing this. This lambda just indicates what lambda value did you use for the estimated loss. Okay. One observation is if you set lambda to 0, right? So in the case that lambda is 0 here, you just get back the original case, like the original problem we've been working with. Okay. And then there's f star. Notice how f star doesn't depend anything on lambdas or anything like that. It's the original thing is it's minimizing the true expected loss. It's going over the actual function class you're working with. Nothing to do with lambdas. Okay. So now we're thinking that we have a fixed function class. Okay. So before we were varying the function class, right? And we were saying like you have more complicated function classes as p changes. Here we're saying fix the function class. Okay. So like maybe I should say, yeah, like we're fixing the function class f. Okay. And now we're thinking about how we change lambda. So usually what you think about doing is you start with a really complicated function class, maybe like degree 10 polynomials, and you'll see this in a plot in a second. So you start with a very complicated function class. And if you set lambda to 0, then you just get back your original predictors that we've been getting, which is a very complicated looking predictor because you don't penalize the weights at all if lambda equals 0. However, as you start increasing lambda, so if lambda increases, then what you will find is that your predictor you output has to get simpler because of this penalization of having large weights. So what really happens is the weights get smaller, like of the predictor, and so that ends up causing the predictor to be simpler. Okay, what does that also imply? Since the expected predictor, right, this guy, is based on the predictor you output, it turns out that the expected predictor also gets simpler. Okay? And the one thing to note is that f star does not change. Okay, so here's the relationship we have. Lambda increasing means that f hat, our predictor, gets simpler, but also the expected predictor also gets simpler. Okay. And so, yeah, so if lambda equals 0, then you end up with these two being equal, but in general, they're not the same. So this is now a case that is different from what we saw before, which is that now the expected predictor is not f star in general. It's only f star if lambda equals to 0. Okay. And how far away these two are is a function of lambda in the way that I described above, which is you increase lambda, these are farther apart. Okay, so then you get this bias variance relationship for regularization, which is that if you look at the bias, which is the following, it's the comparison between expected predictor and F base. What you'll find is that this thing decreases, so it gets smaller as lambda decreases, right? So, and then in the extreme case, if lambda goes to 0, then you have F star. Okay, so that's kind of like the smallest thing you get. And this is exactly from this relationship here. And I wrote it kind of in the backwards way, which is here we saw that if lambda increases, then this gets simpler, and these get farther, so this gets larger. And here we have the other case, which is that this gets smaller if lambda gets smaller. Should make sense as well, like lambda getting smaller means that F bar gets more complex, right, smaller. And so if it gets more complex, then it can get better and better and closer to F base. And in a sense, this is, people say that it's less biased. So it's not so, like, being biased means you're like kind of forced away from the truth. And here this thing is less biased when lambda is small, because it can be closer and closer to F base. Okay. Then there's the variance, which has the opposite situation, like we saw before. So this variance will actually increase if you make lambda smaller. And this should make sense. Making lambda smaller, once again, means you make the function class more complex, or you make the predictor more complex. If the predictor is more complex, then there's the ability for F hat to vary much more from this expected predictor. There's a lot more, in some sense, like variation in what the predictor can look like. And finally, this thing just decreases with n increasing. You increase the number of samples, you're going to just get a better estimate. Okay, that's the relationship. This is what you need to know about regularization and how lambda affects it. You should really think about it as like lambda scaling the complexity of the predictor, and then from there you can fairly easily reason about, is it going to vary more or is it going to be further away from F base? And I can almost assure you there's going to be questions on the assignment and the midterm and stuff about things of like, suppose your lambda is large, like would you expect, or your lambda is increasing, would you expect that the bias increases or the variance increases? And like, if you look at a plot, would you expect this term to look like this or whatever? Okay. Maybe I show the plot. So this is the plot of what you will see, which is now we're plotting lambda. And what you'll see is that as lambda gets smaller and smaller, so notice how I'm doing like the inverse kind of x-axis here. So I'm making lambda smaller and smaller. In this case, you almost have the most, okay, let me mention one thing, which is we're assuming F hat is coming from functions from, like we're minimizing functions, but the function class F10. So this is polynomials of degree 10. In the case that lambda is equal to 0, then you're really outputting like a degree 10 polynomial, which is a very complex looking polynomial. Likely it'll be able to fit or like approximate F base quite well. Okay, so that's, you can think of this as really increasing P in some sense. So yeah, lambda getting smaller means more complex predictors you're outputting. And so what you see is that, similar to before, the training error, this estimated loss on the training data set gets smaller and smaller. Why? Because you're allowing for more complicated predictors. However, what you see is that, once again, this like estimate of the expected loss, this using the test set, will have this type of shape. And so at this point, you have high bias because your expected predictor, like the best kind of predictor you can get is like with this lambda value is very, very simple. So you can barely approximate F base in this case. So this is high bias. And here you have the case where, okay, you have a very complicated predictor. However, since it's so complicated, you let lambda to be very, very small, so it's very complicated. There's a lot of variation between your predictor and the expected predictor. And so you'll find this like high variance problem. And so here, this is really large. This is a very large value because of this high variance problem. And here it's because of the high bias. So there's some nice middle ground that trades off the two of them in the best possible way. And so, okay, so then how do you, in practice, use this thing? Well, what you do is you train your learner, or you use your learner with different values of lambda. And this is actually, so this is what is actually, like, this is almost surely, actually, it was used for like ChatGPT stuff. training and whatever, is they have these things called hyperparameter tuning. So you train your learner with different, what they call hyperparameters, and lambda will be called a hyperparameter. It's kind of like a meta level outside, like above the learner, right? Because you're training a learner for every lambda value. So for lambda of 100, you train one learner, you get a predictor. For lambda 10, you train another learner with that lambda value, and you get another predictor, and so on. Turns out, like sweeping over, like trying these different values of lambda is called trying different hyperparameter values. That turns out in like more complex cases, there's more than just lambda parameter. Well, I can even tell you, like we've talked about these different step sizes. You can imagine also plotting this as like another dimension, having like different step size values. And so you'd be tuning over all these things. For each one of these values of lambda, you get a different predictor, right? So you train a different learner with each one of these. And then on your test set, you look at what its corresponding like value is, and then you pick the best one. So yeah, so you pick the best predictor in terms of this test set. But you really are training different learners. So you train many learners, each one of them outputting different predictors, and then you're picking between those predictors. Okay. Yeah, all that I wanted to say, all that's really left at this point is just like minimizing the regularized loss. Okay. So that's all you have to do. To like, okay, we need to do that, and then when we get that, then we can basically solve for f hat. Okay, so how do we do this? Well, you can derive a closed form solution. I think I'll probably guide you through something like this on the assignment or something. So you can do it. It's actually very similar to like before, but we're going to do the gradient descent version because it's even easier to write that. So what do we need to do for gradient descent? All we need to do is take the derivative of this thing, and then, the gradient. So we need the gradient, and then we just plug it into the gradient descent update rule, right? So this is gradient descent update rule. It's like the weights at epoch t plus 1 are equal to the previous weights minus a step size times the gradient. All we need is this gradient of this function, right? We've seen this a few times already. So let's calculate the gradient of the regularized estimated loss thing. To calculate the gradient, you need to calculate like each one of these partial derivatives. So let's go ahead and calculate the partial derivatives. So how do we do this? Well, let's have a look at what this function looks like. Regularized thing. Recall, and I guess I wrote it above, this thing is just L hat of W. We've seen how to like take the partial derivatives of this thing. So we really are just going to need to take the partial derivatives of this. And I will call this thing like G of W. And it doesn't depend on W0. Okay. So in particular, the partial derivative of the regularized estimated loss with respect to any Wj, okay, that'll be a function of W. Well, that can be thought of as taking the derivative of each one of the parts, taking the derivative of this and this. So we take the derivative of L, just the original L hat, which we've already done. Plus the derivative of this G function I just defined above with respect to Wj. Okay, so this guy, we already know what it is. I'm going to give it to you once we calculate this and we plug it in. So all that's left is to calculate this. So let's calculate this guy. And for this guy, we have two cases. So first, we're going to do the partial derivative of G with respect to W0. So let's do that guy. So this is G. There's no W0 in there. But we should take that derivative anyways, because we want the derivative for every index of W. So what's the derivative of 0 with respect to W0? Well, it's just 0. There's nothing there. So this thing just equals 0. Okay, so that's an easy case. And now what's left is the other case, which is for every other W that's not 0. Okay, and so this is the case, yeah. All right, for J equal to 1 up to D, so not including 0. Okay, so what's this partial derivative here? Well, let's have a look. And I do this fairly quickly. Like you have some constant here. This doesn't really affect the derivative. Remember, the derivative of a sum is the sum of the derivative of the inside term. So all we have left is taking the derivative of wj squared. So for each wj, that's just 2 times wj. So this thing equals to that lambda n, that was just a constant, times 2, okay, I put 2 times wj. Okay, that's all there is to it. So that's your derivative. So then like putting things together, so this is like continuing with this equality. I just give you what this used to be. So you can just look back at the previous optimization stuff. So that thing was 2 times 2 over n, sum I equal 1 to n of this xi transpose w minus yi times xij. Okay, and then we add here the like whatever the derivative is for the different cases. So okay, maybe I write the full thing, which is this partial derivative for w0 is just this, right? That's what we found for, we have these two cases. For w0, it's this, while for wj, it has this extra term, which is this lambda of n 2 times lambda of n wj. And this is for, once again, for j 1 to d. Okay, so that's all there is to it. Like, it's a little bit annoying that you have to do like separate cases. So for like the 0th case, you just don't add this extra little bit of the derivative. And then you have this thing. So then you go up here, you plug these guys into the gradient, and then you do this update. So in code, what you have to do is you have to do like a special case for essentially when w0 equals 0. Or the other way you can think about it is you do this update for all indices except for the 0th index. So you could just apply this update first to everything, right, for all values of w from 0 to j. And then you can apply this part just for the j things, for the j from 1 to d. Anyways, various ways to do this. But it's a little bit annoying that you have to like deal with this extra term after all. But hopefully this makes sense. You're just optimizing over a different objective now. Okay. One thing I just wanted to mention also is that here I've done the minimizing and stuff for the function class f1. Here we didn't have phi's or anything. If you do it with the, once again, with the polynomial features phi, all that changes is that now here you're taking derivatives. Like here you just have a phi. So like you just have this phi that carries around and then you have the phi out. So nothing really changed. You just replace xi's with these phi functions. Yeah. Like the derivative of g is still the same. It doesn't depend on phi. So here you would just get phi of xi. But it's just simpler not to write phi, I guess. And then I guess the other difference is that for wj, you wouldn't have 1 to d. You would have 1 to p bar minus 1 because there's more weights now. Okay. So I leave that as like a, I guess, an exercise. Okay. So that is all I have to say actually about this model, like, predictor evaluation business and so on. Is like, the idea is you're trying to, most of the time, like trade off between complexity of the predictor, because like you would think that you would just pick the most complicated function class or smallest lambda such that you can output the most complicated looking predictor that gives you like the most power. But the problem is you have to trade off with the fact that you can do this, that this issue happens where you start overfitting the data. So if you don't have like enough data, you start fitting the data too precisely, and that means on new data you're not going to predict things well. So, and this is all because of the fact that you only have so much data. So like if your function class is very, like if your predictor can be very, very complicated, you can really, really fit the data super perfectly, but that means on new things you won't do so well. So there's this trade-off between, yeah, complexity of the function class. This is like, what happened now? Now I've lost connection on my computer, which is great. But hopefully I'm still there on my iPad. It does look like that. Okay. I guess let's wait a moment. Or I can, yeah. So is there any questions about that while we try to reconnect here? Okay, so this kind of like, I'm going to say this again, I guess, when we get back online, but this really closes out the, like, a large story of what we've been doing with machine learning, where we decided on an objective, which is to minimize this expected loss, which we hopefully agreed on is a good way to think about how to predict, like, what is like a way to measure how good we can predict new data. And then we talked about how to find a good, like, a learner that makes this objective small, and then how to like evaluate the predictor the learner outputs and pick the best kind of function class for it. Okay. Okay, I'm back now. Oh, I guess, yeah, people online could have still heard me actually. Okay, so yeah, this is like, we did all this. This is kind of the process. This is actually more or less what's done in practice, except all that's really changing is your function class is no longer these polynomials and stuff. They're like these neural networks. So, okay, what does this regularization kind of buy you? Now you're not really stuck with these polynomials and so on. Like, you can make this thing as like this function class as complicated as you want. That's what you kind of like, you start with, make it really, really complicated, like huge, complicated looking nonlinear functions and stuff. And then just have a nice parameter lambda that allows you to tune how complicated the predictor you're going to get learning from this function class. So this is like kind of like a nicer way to tune this thing. Okay, so yeah, this is really quite applicable and stuff. Okay, so what are we going to do next? So what we're going to do next is we're going to think about like, so far we've always talked about this ERM learner stuff. Okay, so okay, there's two kind of things we could do next, which is maybe we could go to talk about classification. Yeah, and I'll answer the question online in a second. Like, we could go into classification, which we will do actually after the reading week for that. And you'll find in classification, like everything's kind of the same. You just change the loss to the 0-1 loss. And then we'll see all the same kind of patterns, and you draw the same things, and everything's nice, and that's like the story's the same. But another thing we can do is we could talk about like not using the ERM learner and using a different learner, and what would happen kind of. So like, why did we choose to, okay, we wanted to minimize the expected loss, which I guess I'm going to get to in a second. And we chose to estimate the expected loss. But it turns out we can estimate other things, like, and maybe I'll make that, that's what I'll do in one second. But maybe let me answer the question first, which is like, just asking, can you explain why decreasing this lambda decreases the bias? Yeah, and so decreasing lambda, you should think about, allows for larger weights. And larger weights, you should think about as allows for more complicated predictors. And if you have more complicated predictors, what you should think about is that, okay, the expected predictor, where is the expected predictor? This expected predictor, f bar, can also be more complicated because it's just the expected predictor based on the f hats, and f hats can be more complicated. And if f bar can be more complicated, then it can be closer to f base. So that's why the bias goes down. Your expected predictor can be closer to the best possible predictor. Okay, so now let's get into what is called maximum likelihood estimation. And in what, like some, wait, this is not the one I wanted. Let's do this guy, the half built in version. Okay, so, and the motivation to think here is that we're going to try to talk about a different way of learning that's not the ERM learner. Okay, so what's another option? So another option, you're going to need to know one piece of, this is not right. Okay, there we go. You're going to need to know one piece of information, which I will give to you, but it starts from this observation, which is that the best we could possibly do is f base, right? This is like the best we could hope for. So why don't we learn what f base is like more directly? We went through this like kind of, okay, what do I mean more directly? So like this is f base, it's the function in the function class that contains all possible functions that minimizes the true expected loss. And what we did is we estimated the expected loss with this like L hat thing, and then we optimized that. Okay, but like it turns out we can like estimate. Okay, one thing we could estimate is like if you write out what L the expected loss is, it has like a distribution over x and y. Right? There was like this thing is based on this thing. Okay, I don't want to write out the thing, but like you remember this thing is like the maybe I write it. This guy, specifically this guy, is written something. Well, it is exactly the expected value of L of f of x y. That's what it is. And this expected value is, so this is over, okay, it's based on what distribution? It's based on the distribution over x and y. So it's based on that distribution. In particular, if you expand out this expected value, you would be using like the PDF or the PMF of x and y. One option is to just estimate that. Why don't we just like get an approximation to that thing instead of getting an approximation to like this thing directly? Why don't we just like estimate the actual distribution? Okay. And we're going to do something almost like that, but we can even make it even simpler than that in some sense by, okay, so if you make an assumption here, okay, so yeah, let me write one form. So like assume, again, squared loss. So if you make this assumption of the squared loss, then what you will find is that if you just expand this thing and plug in the squared loss, and you do a couple steps, which I'll probably also get you to work through in the assignment, what you'll find is that this thing is actually equal to, okay, it's actually equal to, and I write, this will be, so if I write f base and I plug in an x here, right, you'll find that it's equal to the expected value of y, which is the label, conditioned on the random variable x equaling little x. Okay, so you'll find this thing. And we'll expand this in a second to get some understanding about what this thing looks like. But like already this should make some sense. Like the best possible predictor, what does it do? It just predicts the expected value of the label at every single point x. Because remember, at every point x, there could be multiple labels. Like for a house of, let's say, 3 rooms, there could be multiple different prices, right? Depending on different houses. But what you can, like, it turns out the best you can possibly do is just predict the expected value. So like the average house price for houses of 3 rooms. That's what this conditioning means. Okay. Importantly, if you expand this thing, and you did, this is just looking back to the probability chapter and stuff. This is just the integral, and here we're assuming squared loss, okay, and regression. So that's why I'm doing an integral here, because in regression, we're going to assume that like the labels y are the real numbers. So we have an integral y, and it would be this integral y times the conditional PMF or PDF. And in this case, it's a PDF because of the regression setting. So you have the conditional PDF like this, dy. Okay, so this is just the definition of the expected value of y. It's the integral over y times its corresponding PDF conditioned on this corresponding x. If x changes, then the probability of different y values also changes, and you get a different expected value. Okay, so this is like an important formula. So we know f base has this form. So what we're going to do for all of this maximum likelihood stuff is we're going to try to get an approximation of this. Okay, and to fit in what I wanted to write, which is we're going to try to approximate this guy. So in particular, this is what we're going to try to do, which is like, let's use the data set to approximate this guy. Okay, so if we get an approximation of it, what are we going to do? We're going to plug it in here and calculate the integral. Right? So what we're trying to do is really approximate this integral. But to do that, all we need to do is find this. Because like we know what the range y is, just the real numbers, and then we can just integrate. All we need to do is just get an approximation to this. If we do that, we plug it in and calculate this. And guess what? We have an approximation to f base. And so it's going to be quite a quite interesting to see what we get. But in order to see how to do this, we're going to need to do some maximum likelihood estimation basics, which is to see how maximum likelihood, like how do you approximate this guy or estimate it? And then once we get that, then we're going to do that for this and see what we get. Okay, so now we, just like an optimization and other places in this course, we're going to take a slight step back and kind of forget about machine learning world and just talk about general maximum likelihood estimation outside of machine learning, and then we'll come back to how we apply it to this condition. But the thing to keep in mind is that maximum likelihood stuff is trying to get approximations to some PDF, okay, or PMF. Okay, so how does this all look? Yeah, so this is maximum likelihood stuff. Here's the basics. Okay. So maximum likelihood stuff assumes that you have some like data set. And in this case, we have this data set of, you'll see that things look very, very similar to what we have. So we have n samples in the data set, but here we're not saying they're feature label pairs, we're just saying they're random variables z. Okay. And you can imagine you could just plug in feature label pairs into here, but for now it's just some random variable z up to zn. There's some distribution for the data set, and there's some PDF or PMF or some mixture of both complicated looking thing, whatever, that exists. Each one of these is assumed to be IID, which means that they're all independent of each other, and they have the same distribution. So each one of these has the same distribution P of Z, and similarly, that implies they have the same PMF or PDF P of little p of Z. Okay, so what's next? So like, yeah, it asks the question, which is like, yeah, which is basically what we saw above, which is like, if we have a fixed data set, which is what you really have, you don't like, you model this thing as like a random variable, but at the end you get like, just like you get a sample. Like you think of, you get n flips of a coin, you actually flip that coin, and you have those n flips. Now, how am I going to use that to learn what this is, to learn what the PMF or the PDF is for each one of the coin flips? So if you have a fixed data set, calligraphic D, which we'll denote as little z1 to zn, how can we approximate P of z? And you can already see P of z is going to be somewhat, like quite similar to what we wanted above, which is this Py given x. Okay, so how do we do this? Well, in words, it's the following. You're going to pick. Okay, so you need to pick something to approximate P of z. So that thing I'm going to say is P. I guess I'll call it PMLE. It's going to be the thing you pick. It's going to be called PMLE. So we're going to pick PMLE that makes, well, what does it do? It makes the data, or the data set you see, the data, the most likely. Okay, and you'll see what I mean by this most likely second. But here's the idea: is like, you know, you got some observation of these coin flips or this data, whatever, and there's different possible underlying distributions that things could have came from, like that this could have come from. So like, for instance, imagine you see like heads, tails alternating or something like that. Then you want to know, like, what's the underlying, is it a fair coin? Like this is really what I'm asking, is like, is the underlying distribution a fair coin? Is it like a biased coin or whatever? If I see like 10 heads and 10 tails, then probably I'm going to think that like the underlying distribution is like a fair coin distribution. So it's like a Bernoulli with parameter 0.5. This is just like high level. However, if I see like all the heads, then it's probably a good chance that the underlying distribution is not a fair coins distribution, and it's probably something else. So I'm trying to pick the the PDF, but this really, if you have the PDF, you have the distribution. So in some sense, I'm like trying to pick the thing that generated the data, the PDF that gives you the distribution, that makes what the data I see the most likely. Okay. So, okay. So how do I think about this in terms of like mathematically, and as actually finding the thing that makes something most likely and so on, is what I do is I write out what this complicated P of D thing is, right? This is like the PDF, PMF mixture thingy of this random variable. If you write this thing, what you'll notice is that, okay, so this thing is really just this, right? It's like plug in the actual data set. But if you expand the data set, what you'll find is the following. Right? And then you make this wonderful observation, which is that your data was independent. Okay, and if your data is independent, then you know that the PDF, or sorry, like, yeah, data by that, it means each one of these random variables was independent. That means that the PDF can be written as a product of PDFs. In particular, I can write this as P of Z. And okay, I write it a little, like, to make it even more clear. It's like P of the first random variable, Z1, with little z1 plugged in, all multiplied by all the way up to p of zn with little zn plugged in. But they all have the same PDFs. That's what it means to be identically distributed. So this was the independence. So this was independent. And then we use the identically distributed property. And that will tell us that these are all just P of Z, Z1 up to P of Z, Zn. Okay, we're getting places because like what are we doing here? We had data. We know it has some PDF, so we plug that data in. And you can think of this kind of like the probability of that data. It's really going to be like either the probability, like the probability mass, or the probability density. But that this really describes the probability of that data. And it turns out because of these properties, we get to something that looks like this. And I write this with maybe some weird looking notation to you for now, which is there is this product notation. So remember there was like a sum notation, which meant you sum up a bunch of things. Well, notice here these things are multiplied, or when you multiply things, it's called their product. There's a notation for taking the product of n things. So this is the product from I to n. And now instead of summing, you multiply the terms. P of z, zi. Okay. This is nice compressed representation, but more importantly, it emphasizes that the fact that the thing here you don't like that the thing here is that all that you need to understand what this thing is P of z. So you have some like data, you can plug it into this complicated looking mixture thing, but after using these two properties, here it's identically distributed. We use these two properties independent and identically distributed. You get to an expression that looks like this. And this is really nice because now you can see that here you're plugging in like your data, all that it depends on P of z. And what we would like is to pick the like kind of like the PDF or this P of z thing that makes the data the most likely. So here's what we want. We want to find PMLE, and PMLE is going to be equal to the argmax P. Okay. And so this P is like the PDF or PMF I'm searching over that makes this thing the largest. Okay. So let me just interpret this. So this thing you should think of as is exactly equal to the PMF or the PDF of the actual data you got. In the probability mass function case, that's actually exactly equal to the probability of getting that data. In the density case, so like the continuous random, it's actually the density of getting that. But in both cases, you really think about telling you kind of like, here's the word, the likelihood of getting that data, okay? And kind of likelihood is maybe used here because of the fact that it's density or mass, and you can't really say probability. But yeah, it really does tell you the likelihood, so I'll use that word from now on, of getting this data. And it turns out it has this expression. And so like, if we want to find the corresponding P that gives the largest likelihood, well, let's solve this optimization problem. Let's find the P that makes this the largest, makes the data the most likely. Okay, so this is called maximum likelihood estimate, basically, this guy here. Okay, so that's what we want to find. So guess how we're going to find this? We're going to use all the stuff we learned from optimization from before. We're going to plug this guy in, then we're going to take a derivative and set it to 0, basically. But along the way, we'll find that there's some like trickery that makes this a little bit easier. But if you understand this point, you basically understand all of MLE, because then at this point, you just solve an optimization problem, which is everything we've been doing so far. And I'm going to give a couple examples of like what is this? Yeah, like I'll give some examples before we even do the optimization, and then it's just math. Okay. Someone asks like, why is the pairs in the data identically distributed or something? And like, yeah, maybe let me emphasize. So your assumption here is that you have this type of data set and you just assume that these things are IID. Why do you do this? Because you can really write out this stuff and do this you can actually solve the optimization and things like this. If you don't assume this, then these steps don't work and you don't get to here, and we have all sorts of, like everything I say isn't true anymore. But like in machine learning, this is exactly how our data set looks. We have feature label pairs that are IID. So this applies perfectly for us. So we're all good. Okay, so here's the example. Let's think of an example. So like, how do we actually search over something? Okay, we'll get to that in a second. But let's think of an example. So it's the famous coin flipping case. So Zi, each of these are just representing the ith flip of an unfair coin, and in particular, there's some parameter alpha star that describes the unfairness. So like if alpha star is 0.5, you have a fair coin. If it's 1, then there's a 100% chance you get heads. 0 means 0% chance you get heads, and so on. Okay. You can write the Bernoulli PMF in this nice compressed way. Before we wrote it as like this, like if 1, okay, and it's exactly like if Z is 1, right? Z can only be 1 or 0, meaning heads or tails. If it's heads, then you just have alpha star to the 1. So the PMF, the probability is just alpha star. If Z is 0, then this is 1 minus, or sorry, if this is 1, then this thing is 1 minus 1, it's 0, so this thing is just 1, so you're just left with this. And you have the other case, which is if Z is 0, then this thing is 1 here. So the probability of tails would be just 1 minus alpha star, and this term becomes just 1. Okay. Point being that this is just the Bernoulli PMF you've seen before. You plug in the Zs, play around with it, you'll see that it's exactly this case, which is for Z equal 1, you get alpha star. For Z equals 0, you get 1 minus alpha star. Okay. So if we knew that we actually were getting data from coin flips, then we should find a PMF, P, that looks like a Bernoulli PMF, right? This thing has like like an equation, like the equation looks like this. So we're gonna have a function class. And here our function class, I'll use H to not confuse it with like the predictor function class. So here we're really going to be searching over PMFs or PDFs from some function class H. And you'll see how the story is like almost the same as everything before. So we have this function class. Okay, what does it look like? It looks like functions from Z, right? Which is like where each one of these random variables comes from. And it maps to 0, 1, and it has this special form. Before in like predictor world, this thing had a linear function form. Now we have this Bernoulli function form. And guess what? Every single one of these functions is described by a parameter alpha. Similar to how for linear functions and polynomials, every one of them was described by a weight vector W. Okay. So far we need to search over this function class, right? So like, how are we going to search over a set of functions? Well, guess what? We chose this, well, like these, because it's a coin flip, it is a Bernoulli, it has this form. And so a parameter is all you need to do to describe each function. In particular, so like any PMF, P, that's an element of this guy, right, has a corresponding alpha associated to it. I'm going to put in the subscript. So like every single one of them, an element of here. Okay. So let me write it like this. Has the form. So this is, once again, this very important observation, which is every single element of our function class that actually contains functions here has the form alpha to Z 1 minus alpha 1 minus Z. So in particular, it can just be described by a parameter alpha. There's like this one-to-one relationship. Every parameter has a corresponding function in its function class. Guess what? That means we can now just optimize over the parameters instead of functions. So finding this argmax function is going to be equivalent to finding the argmax parameter that describes that function. And so I write that, and we have very, very similar to story. So we have this PMLE thing, which is what we had above, which actually searched over functions in the function class. Well, it turns out that this thing is going to be the same as P of alpha MLE. Okay, so now this is this kind of a function. Makes sense. Like this MLE thing better be a function of this form because it's from this class. And it's described by this guy. And what is P alpha MLE? Well, we just need to know what alpha MLE is, because then we will plug it right into here. And so alpha MLE is going to be basically as you expect. It's going to be the argmax alpha. Okay, what is alpha in Bernoulli? It's either, it's either 0 or 1, or sorry, in this interval 0 to 1. So that's what our optimization domain is, 0 to 1. Right? And what do we want to optimize? We want to optimize this exact same thing we saw before, but for P of alpha for our data points. Excellent. So that says everything I wanted about that. And I want to mention, like, this thing we get back here, right? There is some true PMF here, P of Z. And what are we trying, like, what is this PMLE thing? It's supposed to be an approximation to P of Z, right? There's some true PMF that things are coming from, some true like distribution, and we're approximating with PMLE. So the claim here is going to be that this is approximately equal to P of Z. That's like really our goal. And the way we're going to do it is really find P alpha MLE, where alpha is now the exact same optimization problem as above, except just like in the linear regression case, what we've done is replace searching through functions by searching through parameters that have a one-to-one description of the function. And let me write one more thing, which is this has very special names. Okay. This guy is called the likelihood. Kind of makes sense. It's the likelihood of this data, right? So we're trying to this is why it's called maximum likelihood. You're trying to maximize the likelihood. And sometimes you'll see this, and then this thing, okay. This thing here, instead of having this like subscript alpha and stuff, people will abuse this notation kind of and write something like this. So they'll write P of Zi, and it depends, like, it depends on alpha, right? But alpha is not like a random variable, but people still write this, which is it depends on alpha in this, and they'll write it like this. And you would think that this is like a conditional PMF, but it's not actually a conditional PMF. It's just telling you that it's like depends on this parameter alpha. Yeah, so this is the common notation you'll see in this maximum likelihood notation world, where you write dependence on a parameter, but this parameter is not a random variable or anything. Okay, and similarly, this likelihood, people will write that this is P of D depending on alpha. And that's to describe this whole thing with the product and everything. This would be like this like joint PMF over all of the data. And so people say that they want to maximize the likelihood, P of D, based on this parameter alpha. Okay, now I answer questions. Yeah, so yeah, the question's like, I'm talking about PMFs here. Before I was talking about PDFs. I wasn't actually talking about PDFs. So I said before, this thing is either a PDF or a PMF, doesn't matter. If it is a PMF, well, then we can think about this thing is actually exactly being the probability of the thing in here. But if it's a PDF, then we should think about it as being the density. But it turns out if the density is large, then it also is more likely to be around like that region wherever the density is largest. So it has like that's why we use this word likelihood really. We're going to call this thing this density or probability mass function. We're not going to say we want to maximize the probability. We're going to maximize the likelihood, and the likelihood is going to be this term here essentially. So density. So yeah. To answer the thing, it's like if it's density or mass, we do the exact same procedure, which is we're trying to maximize whatever it is. Like if it's continuous, then you maximize the density. If it's discrete, then you maximize the mass function. Yeah, and like kind of why? Like because both of them decompose in this way. This doesn't depend on being density or mass function. They always, this is just a property that holds for both. And then you can really have this nice form, and then you can optimize this object here. Yeah, yeah. Yeah, so the question is like, why do I take the argmax? Well, I take the argmax because I started with data, and I knew that the data has this like PDF or PMF mixture thingy. And then I wrote out some math, and I got to this point. So I know that the true data has like a PMF or PDF of this form. And so like the most likely the data has some likelihood of appearing or whatever, like getting that data. And it's going to depend on this thing. So if this expression is large, then that means there's a high chance of getting that data for that P. But if this expression is small, then there's a small chance of getting that data. So what I want to do is I want to find basically the P that made the data the most likely of appearing. So that's what the max is. It's searching for the P that would make the data the most likely. I don't know what P it actually came from, but I'm going to pick the one that would make it the most likely. Like it could have totally came from some very, very unlikely P. But the most probable, or maybe like best approximation, is picking the p that really makes this data the most likely, or that's what this approach says. So that's where the max kind of comes from. Yes. So, okay, and to answer the question online, like in the evaluation lecture, the data was IID. The thing that was not IID was the loss functions. So you had loss functions of data, and those were not IID because they had a predictor that depended on data. Okay, I end the lecture here. See you, everyone.